So you never had multivariable calculus, and here I am tossing around this idea of double integrals and triple integrals and even more than that integrals, all with this joint probability distribution stuff. It's all right. You're going to make it. Disclaimer right up front, this video in no way would replace a multivariable calculus course, but we're going to get the integration techniques that we need in order to succeed with our joint probability distributions. Buckle up. All right, here I have a function in two variables. So I have my variables x and y, and I have some bounds for both x and y. So if I wanted to take the integral of this function over the area that's filled by this, we're going to take a look and see what this region looks like that we're integrating in. So I'll have my x and y axis, and I'll have x as 1 up to 3, and I have y as 1 to 2, and we are strictly less than and strictly greater than. And so this is the area that I'm interested in, is inside of this box with all of the edges not actually existing. All right. So if I wanted to know what's happening with my function, now my function would be actually sitting up in a third dimension up above this. So it would be doing something up here. All right. So it's up above that box. And what we want to know is what the volume is, basically, around with that box as its base. So to do that, what we do is we take the integral over that region, and we take it of our f of x, y function with respect to x and with respect to y. Now I can break that region up into just its x components and its y components separately. And when we're thinking about multiple integration, that's what we're going to be doing. So that's what we're going to do. We're going to break our region up into x and y components. Now I'm going to try and color code to make this easier so we know what's working with what. So every time that we're dealing with y, I'm going to make it orange. So since y falls outside of x here, we're going to be integrating with respect to y on the outside of our function. So my first integral will have my y bounds here. So I'll have my 1 and my 2 for my y bounds. And then the dx is inside of that, and so the inner integral will have my x bounds with it. So it'll have my 1 to 3. And then my function inside stays the same. It has my f of x, y function. I'm looking at these bounds. I'm not worried about this elsewhere part because I'm not within that. So with my function, what I'm going to do is I'm going to replace the function with 3x minus y over 9. Now notice I made the x blue and the y orange to correspond with when we're integrating with each of them. So the first thing I'm going to do to make our integration easier is I'm going to notice that the over 9 part of this, my denominator, is through the entire thing. So it's a constant applied to all of the terms in my function. And so I'm going to pull that constant out front so I just don't have to worry about it as I'm thinking through my integration. So I'll have a 1/9 out in front of my integrals, and that leaves 3x minus y inside of my integral. I like to think of this as my inner integral is inside of some unwritten parentheses because that's how we treat it. So instead of saying that they're unwritten parentheses, I add the parentheses to make it super clear what's going on. And then we have to follow the order of operations. So we need to complete what's happening inside of my parentheses first. So inside my parentheses, I'm integrating with respect to x. That means that x is going to be my variable. In this case, only my blue x, right? Only my x matters as a variable. Y doesn't match the variable that I'm integrating with respect to, so y in this case is treated as a constant. So when I integrate with respect to x, I'll end up with 3 times x squared over 2 minus y times x taken over 1 to 3. And again, I can think about this as still being in parentheses because I haven't evaluated it on the 1 to 3 interval yet. So now I'm going to evaluate on my 1 to 3 interval, plugging in 3 first, then subtracting from that, plugging in 1. So now that I've done those substitutions to evaluate over that interval, I no longer have any x variables left in my integral. So the only variables I'm dealing with now are y's. Whenever you're doing one of these, this should happen after you integrate with respect to a variable and you evaluate over the interval. That variable should no longer appear. So now I don't really want to complete this integral the way it's written because it's very messy and it's not simplified at all inside. And so I'm going to simplify what's inside of the parentheses to make my integral look a little bit nicer and cleaner to complete. So now that I've completed a couple of simplifying steps, I'm left with just the integral from 1 to 2 of 12 minus 2y dy. And I can take this just like I did in single variable calculus. Y is my variable, so that's what I'll treat as my variable as I integrate. So now that I've done that integration, I simply have to evaluate it over the interval 1 to 2. Now that I've evaluated it over the interval, it looks very messy because I haven't simplified anything, but I have no variables left. So when I simplify this down, I'll simply have a number, which is the answer to my double integral. So after performing all of my arithmetic steps to simplify that down, I'm left with my double integral was 1. So let's consider another function in x and y. This one's going to equal 24xy when 0 is less than or equal to x is less than or equal to 1, 0 is less than or equal to y is less than or equal to 1, and x plus y is less than or equal to 1. Whenever you have a bound that's given to you and it has an equation in it, it's a very good idea to draw the plot to see what this will look like, what this region looks like. So I'm going to have my x and y axis. Each are going to go from 0 to 1. And my x variable is going to go from 0 to 1. So x will go from 0 to 1. My y variable will go from 0 to 1. And then I have this equation here, x plus y is less than or equal to 1. So I'm actually going to plot the line x plus y equals 1. And that line is going to be the straight line from y equals 1 to x equals 1, where the other is 0 each place. And these sums will be less than when we are on this side of the line. So I'll be going this way for this inequality. My x inequalities tell me that I'm going between this way. My y inequalities tell me that I'll stay between 0 and 1 going this way. And so my entire region that I'm looking at is actually this triangle here. Now, if we try to make bounds the way that we did before, we would make a square. The bounds with a whole number each place always result in a square. So I'm going to set up my double integral. I know that I'm going to be integrating twice, and I know that one of them is going to be with respect to y, and I know that one of them is going to be with respect to x. And to keep things easy, I'm going to keep them in the order that I'm going to integrate with respect to x first, and then with respect to y. So whenever you have something like this, the bounds on your outer integral, so in this case, my integral with respect to y, they need to be numbers. You need to keep those as numbers, because otherwise we'll end up with an integral after we do our substitution over the interval that ends up with variables involved, and we don't want that to be the case. So we're going to integrate from 0 to 1 with respect to y. So our y region is going to cover this, which covers the bottom of our triangle, but not the top. So that's going to be left to our x bounds. So what we do is we look at x in terms of going left to right. So our lower x bound is our leftmost x value, and notice that is a straight line, straight vertical line at x equals 0. So we actually can use a 0 as our lower bound for x. However, we can't use the 1 that's given to us as an upper bound for our x values, because that would complete this rectangle and give us an entire triangle we don't want. So what we instead need is this line right here in terms of x. So to do that, we're going to take the equation that is that line. So x plus y is less than or equal to 1. And we're going to solve this for x. So all I do is I subtract y from both sides, and I'll end up with x is less than or equal to 1 minus y. And this is exactly an upper bound for x. 1 minus y is as large as it can get. So I'll have 1 minus y as my upper bound for my x values. And this is okay because y is a variable, but notice it's that variable that's going to get replaced when I do my integration when I do my second integration. So let's see how this plays out when we integrate. So I'm going to plug in my function 24xy, and now I'm going to integrate it the way I did before. So remember, I have the parentheses that aren't written, but I'm going to write them. And I'm going to integrate what's inside of my parentheses. But before I do that, I'm going to notice that 24 is a constant, and it's being multiplied by everything that I'm integrating. And so I'm going to pull the 24 out front to make this easier along the way. So now I'm ready to integrate what's inside of my parentheses. So I'm going to do that. And now that I've integrated, I'm going to evaluate it on my interval. So I'm going to plug in 1 minus y everywhere I have an x, and then I'm going to subtract from that, plugging in a 0 everywhere I have an x. And now, again, I only have y's as variables inside, so I'm down to a single integral with a single variable. But again, it's not an integral I want to take because it's super messy inside, and I can do a lot of simplification there. So let me do that. And now I can simplify it even more, noticing that the denominator of 2 is applied to everything in there. And so I'm going to pull that out front with the 24 as well. And now I have everything simplified, so I'm ready to integrate with respect to y. And again, this looks like a single variable calculus version of an integral, so hopefully you have lots of practice doing those. So now I have my integral, and I just need to evaluate it over the interval from 0 to 1. I'll plug in 1, and then I'll subtract from that, 0 plugged in. And now I'm down to only numbers, so I just have to do some arithmetic and simplification, and I'll have my answer. And once I've done all of that simplification, I end up with 4 as my answer. Now, you can do this with more than just 2 integrals. You just keep nesting them one inside of another, and you can actually do this for as many integrals as you need to.